Hey everyone! Today we're going to tackle a really cool geometric puzzle. Now, it might look a little complicated at first glance, but I promise you, the solution is all about looking at the problem in just the right way. So, let's dive right in.
Okay, so here's our setup. We've got a circle, we've got a fixed line called L2, and we have 2 points A and B that are on that circle. Then there's this other point P that can slide anywhere it wants along line L2. Our mission, should we choose to accept it, is to find the absolute minimum value of the inner product of the vectors PA and PB. Now, I know what you're thinking. Inner product, vectors, that sounds pretty technical, but don't worry about it. The solution is actually really visual, and we're going to break down exactly what that term means in a way that just makes sense.
So, to crack this thing open, we first need to get comfortable with the main tool we'll be using, the inner product. But instead of getting bogged down in a bunch of formulas, we're going to find a much simpler, more intuitive way to think about what it's actually doing. So, what is this inner product thing? You might also know it as the dot product. Well, it's just a special way to multiply two vectors together. And the number you get at the end isn't just random, it's a measurement. It tells you how much those two vectors are on the same page, how much they're pointing in the same general direction. And this, right here, this is the secret. Seriously, forget the math for a second and just think about this analogy. The inner product is basically like the shadow that one vector casts onto another. Imagine the sun is directly above them. The length of that shadow tells you pretty much everything you need to know. And this illustrates the idea perfectly. Look, when two vectors are pointing in almost the same direction, that shadow is really long, right? That means the inner product has a large value. But as the angle between them gets wider, the shadow shrinks, and the value of the inner product gets smaller and smaller. This shadow concept is literally the key to solving our entire puzzle. Okay, so let's run with that shadow idea. Our goal is to find the minimum possible inner product. So the challenge becomes pretty simple, doesn't it? How do we arrange our points to make that shadow as short as it can possibly be? So here it is, the big question. If we want the absolute smallest value, what's the most efficient, most direct setup? Think about it visually. How could we possibly line up P, A, and B to make that shadow, well, to make it as minimal as possible? And the answer is a perfectly straight line. It's that simple. Any kind of angle between the vectors PA and PB is just going to create a longer shadow, a bigger value. To get the most efficient, most extreme value, we need them to be perfectly collinear. That just means lined up on the exact same straight path. Now that we know our solution has to involve a single straight line that cuts through P, A, and B, the problem has totally transformed. It's not really about vector angles anymore. Now, it's all about finding the shortest possible line that connects our circle to that line L2. And here's where we lean on a fundamental rule of geometry. The shortest distance from any point to any line is always the path that's perpendicular to it. It's the one that hits it at a perfect 90-degree angle. So, our perfect line, the one with P, A, and B on it, has to be the one that goes right through the circle's center and hits L2 at that 90-degree angle. Okay, so let's actually calculate that shortest distance. First step, we grab the circle's center, which we can see is at the coordinates 1, 2. Then we just use the standard point-to-line distance formula. It might look a little intimidating, but it's really just a recipe. You take the numbers from the lines equation, you take the coordinates of your point, you plug them in, and it spits out the exact perpendicular distance. It's pretty much a plug-and-play calculation from here. And when we run the numbers, we get exactly 3. Boom. This number is absolutely crucial. This is the shortest possible distance from the very heart of our circle to the line where our point P lives. All right, we've done all the hard work. We figured out the key geometric idea, collinearity, and we've calculated that critical distance. Now let's just put all the pieces together and find our answer. So here's our whole perfect line situation all laid out. The distance from the circle's center all the way to point P is 3. We just calculated that. We also know the circle's radius is 2. So the distance from P to the closest point on the circle, which is A, is just 3 minus the radius, which is 1. And the distance to the farthest point, B, is going to be 3 plus the radius, which is 5. And this is the most beautiful part of the whole thing. Because P, A, and B are all on that perfect straight line, our whole shadow analogy becomes reality. The shadow is just the full length of the vector itself. That entire complex-sounding idea of an inner product just simplifies down to multiplying the two lengths together. How cool is that? So to get our minimum value, we just multiply 1 by 5, which equals 5. And that's it. That's our answer. A clean, simple number that we found not with crazy formulas, but with a pure geometric insight. You know, what this problem really shows us is something much bigger than just some circles and lines. It really opens up a powerful way of thinking about mathematics in general. So what are the big lessons here? Well, first, try to visualize your problem. Turn those abstract equations into pictures in your head. Second, find simple analogies like our shadow trick to really get a gut feeling for complex ideas. And finally, always be on the lookout for the simple, elegant geometric truth that's often hiding inside a complicated-looking problem. And that leaves us with one final question to think about. Today, we used a geometric picture to solve a vector problem. But what other complex ideas, maybe in math or physics or even something like data science, could suddenly become crystal clear if only we just tried to draw the picture first? Something to think about. That's all for this explainer. Thanks for joining me.